For most of human history, the ocean floor did not exist in any practical sense. It was not seen, not measured, not described in maps or drawings. It lay beneath miles of water, hidden by darkness and pressure, separated from daily life by a barrier that could not be crossed. People sailed across the surface of the seas for thousands of years, navigating by stars and coastlines. Yet the vast landscape below their ships remained entirely unknown. Welcome to another calm documentary to help you sleep. Tell us in the comments, where are you listening from, and what time is it there? We hope this narration will ease your mind. If it does, please consider subscribing. Let's continue. On land, mountains could be climbed and valleys could be walked. Even distant deserts and polar regions could eventually be reached with enough effort. But the deep ocean resisted all simple attempts at exploration. Light fades quickly in water. Within a few dozen meters, colors begin to disappear. Reds vanish first, then oranges and yellows. As depth increases, the world turns blue, then dim, then completely black. By the time one descends a few hundred meters, sunlight is gone. Beyond that point, the sea becomes a place without natural illumination. This absence of light was only the first barrier. Pressure increases steadily with depth. For every 10 meters of descent, the weight of the water above adds another atmosphere of pressure. At a depth of 1,000 meters, the pressure is roughly 100 times greater than at the surface. At the deepest ocean trenches, more than 10 kilometers down, the force becomes immense. Human bodies cannot withstand such compression. Even sturdy materials deform and collapse under those conditions. For centuries, this physical reality made direct exploration impossible. As a result, early thinkers relied on assumption rather than observation. Many believed the seafloor must be relatively flat and featureless, perhaps covered in fine sediments that settled slowly from above. The ocean was imagined as a vast basin, its bottom smooth and uniform, like the floor of a shallow pond, but on a much larger scale. Without evidence to contradict this view, it seemed reasonable. Ancient philosophers speculated about the nature of the deep, but their ideas were shaped by limited information. Sailors occasionally lowered weighted ropes to estimate depth near coastlines, especially in harbors or along trade routes. These soundings were practical tools for navigation. They revealed that the seafloor near land could be uneven, with shoals and channels. Yet beyond the continental shelves, where depths increased dramatically, measurements were rare and often inaccurate. The open ocean remained a blank space. Even during the age of exploration, when ships crossed entire oceans, knowledge of what lay beneath remained minimal. Mariners charted currents and winds. They recorded coastlines and islands. They improved their understanding of global geography above water. Still, the bottom of the sea was treated as an abstract boundary, the unseen foundation of the oceans, rather than a landscape in its own right. The difficulty was not a lack of curiosity, it was a lack of tools. To know the shape of the seafloor required some way to measure depth systematically across vast distances. Lowering a rope with a weight attached was slow and limited. In deep water, the rope itself became heavy and difficult to manage. Currents could carry it sideways, introducing errors. A single measurement might take hours. To map an entire ocean basin this way would require an unrealistic amount of time and labor. Meanwhile, scientific knowledge on land continued to advance. By the 18th and 19th centuries, astronomers were carefully charting the surface of the moon. Through telescopes, they identified craters, plains, and mountain ranges. Detailed lunar maps were drawn, showing features that no human had ever touched. It is a quiet irony that, at that time, the contours of the moon were better understood than the terrain beneath Earth's own oceans. This contrast gradually became more noticeable. As geology developed as a discipline, scientists began to ask broader questions about the structure of the planet. Mountains and continents were studied in detail. Fossils were cataloged. Rock layers were examined and compared across regions. Yet more than half of Earth's surface lay hidden underwater. Without knowledge of the seafloor, any understanding of the planet remained incomplete. There were also practical motivations. Submarine telegraph cables, introduced in the 19th century, required knowledge of the ocean bottom. Engineers needed to know where cables might rest safely and where steep slopes or rough terrain could cause damage. This technological need provided a new reason to investigate the deep. Still, in the early 1800s, the ocean depths were often imagined as lifeless voids. The combination of darkness, cold, and pressure seemed too extreme to support living organisms. Some naturalists proposed that below a certain depth, life simply ceased to exist. The seafloor was pictured as a quiet desert, covered in fine mud, undisturbed except by the slow settling of particles from above. The invisibility of the deep ocean shaped these assumptions. Humans are accustomed to learning through sight. When a landscape cannot be seen, it is difficult to conceive of its details. The ocean surface, with its shifting waves and changing colors, offered no clues about what lay thousands of meters below. It appeared uniform, a moving boundary that concealed rather than revealed. Gradually, careful measurements began to challenge simple ideas. Isolated deep soundings suggested that some parts of the ocean were far deeper than expected. Variations in depth hinted that the bottom might not be flat after all. These early findings were scattered and incomplete, but they introduced uncertainty into the prevailing view. The mystery of the ocean floor became more defined through these small observations. Scientists recognized that an enormous portion of Earth's surface remained unmapped. It was not simply unexplored territory in the traditional sense. It was territory that could not even be directly observed. The challenge was both physical and conceptual. By the mid-19th century, a quiet determination began to form within parts of the scientific community. If the ocean floor could not be seen, it would have to be measured indirectly. New methods would need to be developed. Instruments would have to withstand depth and pressure. Ships would have to travel systematic routes, recording data point by point across open water. This emerging effort did not begin with dramatic discoveries. It started with patient curiosity. The recognition that something vast and unknown lay beneath familiar sea routes created a steady motivation to learn more. The ocean floor, once imagined as a simple boundary, was slowly becoming an object of study in its own right. At this early stage, the deep sea remained silent and dark, its contours hidden. Yet the idea that it might contain mountains, valleys, and structures as complex as those on land had begun to take shape. The mystery was no longer accepted as permanent. It was understood as a problem waiting for methodical investigation. For many centuries, the only practical method for measuring the depth of the sea was simple and direct. Sailors used what became known as the lead line. It was a rope, often marked at regular intervals, with a heavy weight attached to one end. The weight was usually made of lead, dense and compact, able to sink quickly through the water. The rope was lowered over the side of a ship until the weight touched the bottom. The length of rope paid out gave an estimate of depth. This method was not designed for scientific curiosity at first. It was a navigational tool. Ships approaching coastlines needed to know how much water lay beneath their hulls. In shallow waters, unseen sandbanks or rocks could damage or sink a vessel. By measuring depth repeatedly as they approached land, sailors could detect rising seabeds and adjust their course. The lead line became a routine instrument of maritime life. The rope was marked in fathoms, a unit based on the span of outstretched arms, roughly 6 feet. Knots or pieces of cloth were tied at known intervals so that sailors could count depth by touch, even at night. The process required coordination. One crew member would cast the weight forward into the water as the ship moved slowly ahead. As the line descended, it was allowed to run freely through the hands. When the weight reached the bottom, the rope slackened. The depth was then called out and recorded if necessary. In shallow coastal regions, this system worked well enough. Depths were moderate, and the time required for each measurement was manageable. However, as ships ventured farther from shore, the limitations became clear. In deep water, lowering a rope hundreds or thousands of meters long was slow and physically demanding. The weight of the rope itself increased as more of it entered the water. Currents could pull the line at an angle, causing inaccurate readings. Wind and waves added further complication. Despite these difficulties, occasional deep soundings were attempted. In some cases, explorers lowered lines thousands of meters into the ocean. The task could take hours. The rope might drift far from the ship's vertical position. When the weight was finally retrieved, it sometimes brought back a small sample of material from the seabed. To make this possible, sailors often hollowed out the bottom of the lead weight and filled it with tallow, a soft animal fat. When the weight touched the ocean floor, small amounts of sediment adhered to the tallow. Upon retrieval, the material could be examined. Sand, mud, shell fragments, or fine silt provided clues about the nature of the bottom in that location. These samples were modest in size, often no more than a thin coating. Yet they carried quiet significance. They showed that the ocean floor was not uniform everywhere. In some places, coarse sand suggested stronger currents. In others, fine mud indicated calmer conditions where particles settled slowly over time. Fragments of shells hinted at biological activity, even at surprising depths. The process remained slow and geographically limited. A single sounding represented only one point in an immense expanse. Between measurements lay vast distances with no data at all. Nevertheless, as ships crossed oceans repeatedly along trade routes, scattered soundings accumulated. Gradually, patterns began to emerge. Some measurements revealed depths far greater than previously imagined. Where sailors had assumed a gradual, gentle slope from continental shores into deeper water, they instead found sudden increases in depth. In certain regions, the line seemed to descend almost endlessly before reaching bottom. These results were sometimes met with skepticism. It was difficult to trust measurements taken under challenging conditions, especially when they contradicted comfortable assumptions. Errors were common. Ropes stretched under their own weight. Currents pulled lines sideways. In very deep water, it was not always clear whether the weight had truly reached the bottom or simply stopped descending due to resistance in the line. Yet even with these uncertainties, the overall trend was becoming clearer. The ocean floor was not a simple, shallow basin. It was deeper and more varied than expected. By the early 19th century, improvements in rope materials and measurement techniques allowed somewhat more reliable deep soundings. Naval expeditions, often motivated by exploration or commerce, began recording depths more carefully. Data were logged systematically rather than casually noted. This shift marked the beginning of a more scientific approach. The expansion of global trade and communication added further motivation. When submarine telegraph cables were proposed to connect continents, engineers faced a practical question. Where exactly would these cables lie? If the ocean floor were rugged, cables might snap or become damaged. If it were relatively smooth, long-distance communication might be feasible. Reliable depth measurements became economically important. In response, more organized surveys were undertaken. Ships were assigned to specific routes, lowering lead lines at regular intervals across wide stretches of ocean. Each sounding required patience. The vessel slowed or stopped. The weight was lowered carefully. The crew waited as the line descended through cold, dark water. When the measurement was complete, the rope was hauled back by hand. The repetition of this process, day after day, produced a growing body of data. When plotted on charts, these soundings began to outline unexpected shapes. In some regions, the depths formed long depressions, deeper than surrounding areas. Elsewhere, soundings suggested underwater elevations, rising from the abyss. The notion of a flat, featureless seabed was becoming increasingly difficult to maintain. One of the most significant transitions occurred when expeditions shifted from isolated measurements to systematic mapping. Instead of recording depths only when convenient, surveyors began following planned lines across the ocean, spacing their soundings at regular intervals. This approach allowed scientists to compare measurements in sequence and detect trends, rather than isolated anomalies. As more data accumulated, it became evident that the ocean floor contained structures on a grand scale. Although still inferred indirectly, these features hinted at ridges, basins, and slopes. The deep sea, once imagined as uniform and quiet, appeared more complex. Each new measurement added a small piece to a slowly forming picture. These early efforts remained constrained by the limitations of the lead line. The process was labor-intensive and slow. Large areas of the world's oceans remained unsounded. Yet the fundamental idea had changed. The seafloor was no longer regarded as unknowable. It was a terrain that could, with sufficient patience, be measured and mapped. By the middle of the 19th century, scientific expeditions began to incorporate oceanography as a distinct objective. Ships were equipped not only for navigation, but for data collection. Depth soundings, sediment samples, temperature readings, and biological specimens were gathered together. The ocean was becoming a subject of systematic study, rather than a mere route for travel. The gradual accumulation of lead line measurements did not produce dramatic revelations overnight. Instead, it created a steady shift in understanding. The ocean floor revealed itself point by point, each sounding a small act of inquiry lowered into darkness. From these patient efforts emerged the first outlines of a hidden landscape, setting the stage for more advanced techniques that would soon transform how the depths were explored. In the early years of the 20th century, a quiet transformation began in the way humans measured the ocean. The lead line, though reliable in shallow waters, was too slow for broad exploration. The need for a faster and more precise method became increasingly clear. Part of this urgency arose during the First World War, when submarines introduced new challenges beneath the sea surface. Detecting objects underwater required a better understanding of how sound behaves in water. Sound travels differently in water than in air. Because water is denser, sound waves move faster and over longer distances. A disturbance, such as a pulse generated by a mechanical device, spreads outward in all directions. If it encounters a solid surface, part of that energy reflects back toward its source. By measuring the time between sending a sound and receiving its echo, one can estimate the distance to the reflecting surface. This principle became the foundation of echo sounding, later known more broadly as sonar, an acronym for sound navigation and ranging. Early systems were simple by modern standards. A device mounted on the hull of a ship would emit a brief pulse of sound directed downward. The pulse traveled through the water column until it struck the ocean floor. The returning echo was detected by a receiver. The elapsed time, combined with knowledge of the speed of sound in seawater, allowed depth to be calculated. The process was efficient. Instead of lowering a rope and waiting for it to reach the bottom, a ship could measure depth in seconds. As the vessel moved forward, it could send repeated pulses at regular intervals. This allowed for nearly continuous depth readings along a ship's path. The seafloor, once sampled point by point with great effort, could now be traced in a steady line. The early echo sounders produced simple records. On paper charts, the returning signal was marked as a line corresponding to depth. As the ship progressed, the record formed a profile of the seafloor beneath it. Where the bottom was level, the line remained steady. Where it rose or fell, the line shifted accordingly. Gradually, these profiles revealed shapes that had never been imagined in detail before. As more vessels adopted echo-sounding technology in the 1920s and 1930s, oceanographers began to assemble longer transects across entire ocean basins. These profiles did not suggest flat plains, extending without variation. Instead, they showed hills, steep slopes, and deep valleys hidden beneath thousands of meters of water. The seabed appeared rugged, more comparable to mountainous landscapes on land than to a smooth basin. One of the most significant revelations emerged in the Atlantic Ocean. Repeated echo soundings along routes between Europe and the Americas began to show a broad, elevated structure running roughly north to south along the center of the ocean. This feature rose thousands of meters above the surrounding abyssal plains. It extended for great distances, forming what came to be known as the Mid-Atlantic Ridge. Although not fully understood at first, its scale and continuity suggested that the ocean floor possessed organized structures rather than random irregularities. At the same time, soundings in the Pacific Ocean revealed regions of extraordinary depth. In certain areas, the echo returned after much longer intervals than expected. These measurements indicated trenches descending far deeper than typical ocean basins. The Mariana Trench, for example, was identified as one of the deepest parts of the global ocean. Such trenches reached depths exceeding 10 kilometers, far beyond earlier assumptions. These discoveries gradually altered scientific understanding of Earth's structure. The ocean floor was not simply a passive boundary beneath water. It contained vast ridges stretching across oceans, deep trenches bordering continental margins, and expansive plains in between. The scale of these features rivaled that of continents and mountain ranges on land. Echo sounding also revealed flat regions known as abyssal plains. These areas, covered by fine sediments, extended for hundreds or even thousands of kilometers with minimal variation in depth. Their smoothness contrasted with the dramatic slopes of ridges and trenches nearby. The coexistence of flat plains and steep features added complexity to the emerging picture. The technology itself continued to improve. More precise timing devices allowed for greater accuracy in depth calculation. Better understanding of how temperature and salinity affect the speed of sound in seawater refined measurements further. Oceanographers recognized that sound does not travel at a single constant speed in all conditions. By accounting for variations in water properties, they could adjust calculations and reduce errors. As the number of recorded profiles increased, patterns became clearer. The Mid-Atlantic Ridge was not an isolated structure, but part of a global system of underwater ridges extending through multiple oceans. Trenches often appeared near the edges of continents or island chains. Seamounts, underwater volcanic mountains, rose abruptly from the deep. Some were tall enough to approach the ocean surface without breaking through. These features suggested that the seafloor was shaped by geological processes. Although the theory of plate tectonics had not yet been fully developed, the evidence from echo sounding laid essential groundwork. The ocean floor appeared dynamic rather than static. Its ridges and trenches hinted at movement and change over long timescales. The shift from lead line measurements to sonar mapping marked a profound transition. For the first time, scientists could visualize continuous stretches of the seabed. The darkness of the deep ocean remained, and direct observation was still rare. Yet through sound, a detailed outline of the hidden landscape began to emerge. By the mid-20th century, ships equipped with echo sounders had traced extensive portions of the world's oceans. Each voyage added new lines to charts, gradually filling in blank areas. The once invisible terrain beneath the waves was becoming measurable, describable, and increasingly understood. The ocean floor, long considered remote and unknowable, was revealing itself as a structured and varied part of the planet's surface. As sonar surveys expanded across the world's oceans, the growing collection of depth profiles began to resemble pieces of a very large puzzle. Individual lines recorded by ships were useful on their own, yet their full meaning emerged only when compared and combined. Oceanographers gathered records from different voyages and plotted them carefully onto charts. Over time, a broader pattern became visible. The mid-ocean ridges, first recognized in the Atlantic, were found to extend into other basins. Similar elevated structures appeared in the Indian Ocean and across vast stretches of the Pacific. When these ridges were traced on global maps, they formed a continuous network encircling the planet. The system resembled a long chain of underwater mountains, rising from the depths and stretching for tens of thousands of kilometers. These ridges were not sharp peaks like many mountain ranges on land. Instead, they were broad swells in the ocean floor, often with a central valley running along their crests. Echo-sounding profiles showed that the seafloor sloped upward gradually toward the ridge, then descended again on the opposite side. The symmetry of these profiles attracted attention. It suggested that the ridges were not random accumulations of material, but parts of a coherent geological process. At the same time, deep ocean trenches were mapped with increasing precision. These long, narrow depressions often lay near the edges of continents or adjacent to chains of volcanic islands. Their depths were remarkable, reaching far below the surrounding seafloor. Sonar measurements showed steep sides descending into elongated basins. In some cases, trenches ran parallel to coastlines for thousands of kilometers. As more data accumulated, scientists began comparing the distribution of earthquakes with the locations of ridges and trenches. Seismic activity often clustered along these underwater features. Earthquakes were not evenly distributed across the globe. Instead, they tended to follow the same lines traced by sonar mapping. This alignment hinted at an underlying connection between the shape of the ocean floor and the forces shaping the planet. During the mid-20th century, new techniques complemented echo sounding. Marine magnetometers, instruments designed to measure variations in Earth's magnetic field, were towed behind research vessels. As ships crossed mid-ocean ridges, they recorded alternating patterns of magnetic intensity in the seafloor rocks. These patterns appeared as symmetrical stripes on either side of the ridge axis. Careful analysis revealed that these magnetic stripes corresponded to periods when Earth's magnetic field had reversed direction in the distant past. When molten rock emerged along the ridge crest and cooled, it preserved a record of the magnetic orientation at that time. As new material continued to rise and solidify, older sections were gradually pushed outward. The symmetrical magnetic patterns provided evidence that the seafloor was spreading apart from the ridge. This idea, known as seafloor spreading, offered a methodical explanation for the structure observed in sonar maps. At mid-ocean ridges, new oceanic crust formed as magma rose from beneath Earth's outer layer. As it cooled and solidified, it moved slowly away from the ridge, making space for additional material. The ocean floor was not static. It was being created continuously along these underwater mountain chains. The presence of deep trenches required a complementary process. If new crust was forming at ridges, older crust must be removed elsewhere to maintain balance. Sonar maps showed that trenches marked regions where the seafloor descended sharply into Earth's interior. These areas became known as subduction zones. There, oceanic plates sank beneath adjacent plates, gradually returning material to deeper layers of the planet. The concept of tectonic plates emerged from the integration of these observations. The Earth's outer shell was understood to be divided into large, rigid segments. These plates moved slowly over geological timescales. At mid-ocean ridges, plates diverged and new crust formed. At trenches, plates converged and one descended beneath another. The mapping of the ocean floor provided crucial evidence for this framework. The development of global bathymetric maps required careful compilation. Individual ship tracks were combined into larger grids. Where gaps existed, additional surveys were conducted. The work demanded patience. Each voyage added only narrow strips of data. Yet over decades, these strips accumulated into coherent representations of entire ocean basins. As the maps became more complete, the ocean floor revealed itself as a landscape with structure and organization. Long ridges, deep trenches, fracture zones, and vast plains formed a connected system. The arrangement of these features corresponded with patterns of earthquakes, volcanic activity, and continental movement. The data supported the view that Earth's surface was in continuous, gradual motion. This shift in understanding was not sudden. It developed through incremental evidence. Sonar profiles showed topography. Magnetic measurements indicated spreading. Seismic records outlined zones of interaction. Together, these independent lines of information formed a consistent picture. The ocean floor, once assumed to be stable and unchanging, was now recognized as active and evolving. Mapping the seafloor altered the broader perception of the planet. Continents were no longer considered fixed in place. Instead, they were parts of moving plates. Oceans were not permanent basins, but dynamic regions where crust was created and destroyed. The hidden terrain beneath the sea had provided key insight into Earth's fundamental processes. By the latter half of the 20th century, detailed bathymetric charts covered large portions of the globe. The outlines of ridges and trenches were well established. Although many smaller features remained to be mapped, the overall structure of the ocean floor had been revealed in considerable detail. Through steady measurement and careful interpretation, the once invisible depths had become central to understanding how the planet changes over time. As the 20th century progressed, sonar systems became more refined. Early echo sounders had measured depth directly beneath a ship, producing a single line of data along its path. While useful, this approach left wide areas between ship tracks unmapped. To build more detailed representations of the seafloor, broader coverage was required. This need led to the development of multibeam sonar. Unlike single beam systems that send one pulse straight downward, multibeam instruments emit a fan-shaped array of sound waves that spread outward across the seafloor. Each pulse covers a wide swath beneath the ship. As echoes return from different angles, the system calculates depth across a broad strip rather than a single point. With each pass, a vessel can map a corridor of terrain many kilometers wide. The principle remains the same as early echo sounding. A sound pulse travels through water, reflects from the bottom, and returns to a receiver. The difference lies in geometry and computation. Modern systems use arrays of transmitters and receivers, along with precise timing and positioning tools. Global navigation satellites provide accurate location data for the ship, ensuring that each measurement is placed correctly on a map. Computers process thousands of returning echoes in real time, converting them into detailed bathymetric grids. The results are precise. Underwater mountains, canyons, landslides, and volcanic cones appear with clarity. The shapes of mid-ocean ridges and trench walls can be rendered in 3 dimensions. Subtle features, such as sediment waves shaped by deep currents, become visible. The ocean floor, once traced in thin lines, now emerges as textured terrain. Even so, ships equipped with multibeam sonar must physically travel across the areas they measure. The global ocean is vast, covering more than 70% of Earth's surface. Survey vessels move at modest speeds, often mapping only a few tens of kilometers per day. Large regions remain unsurveyed simply because they have not yet been crossed in systematic patterns. To extend mapping beyond ship tracks, another method has proven valuable. Satellites orbiting Earth can measure the height of the ocean surface with remarkable accuracy. Instruments on board these satellites send radar pulses downward and record the time it takes for the signal to reflect back from the sea surface. By repeating this process continuously, they detect variations in sea level measured in centimeters. At first, the ocean surface might appear smooth on large scales. In reality, it is subtly shaped by gravity. Massive underwater features, such as seamounts or ridges, exert a slightly stronger gravitational pull than surrounding regions. This pull draws a small amount of water toward them, creating a gentle bulge at the surface above. Conversely, deep trenches produce slight depressions in the sea surface. These variations are too small to notice without instruments, yet satellites can detect them. By analyzing these patterns of sea surface height, scientists infer the presence of structures below. Satellite altimetry does not provide the fine detail of multibeam sonar, but it offers near global coverage. It reveals the broad outlines of ridges, fracture zones, and trenches, even in remote parts of the ocean where ships have not yet conducted detailed surveys. In this way, space-based measurements complement ship-based mapping. Autonomous underwater vehicles, often called AUVs, represent another advance. These robotic craft can travel close to the seafloor, carrying high-resolution sonar systems and cameras. Because they operate nearer to the bottom than surface ships, they produce exceptionally detailed maps of specific areas. IUVs are particularly useful for studying mid-ocean ridges, hydrothermal vent fields, and submarine canyons. Their movements are carefully programmed, and they navigate using acoustic signals and onboard sensors. Remotely operated vehicles, connected to research vessels by cables, also contribute to mapping and observation. While their primary role often involves visual study and sample collection, they carry sonar instruments that refine local bathymetry. Together, these technologies allow scientists to examine both the large-scale structure of ocean basins and the fine details of individual formations. Despite these advances, a significant portion of the ocean floor remains only partially mapped at high resolution. Satellite data provide a broad framework, but detailed multibeam coverage extends over a smaller fraction of the seabed. The scale of the task is considerable. Surveying the entire ocean with fine resolution requires time, resources, and coordinated international effort. In recent years, global initiatives have aimed to accelerate this work. Research institutions and hydrographic agencies share data to assemble more complete maps. Each expedition contributes new strips of information, gradually filling gaps. The process is steady rather than dramatic. Ships follow planned routes. Sonar pulses descend and return. Data are stored, processed, and added to collective archives. The ocean floor continues to change slowly through tectonic movement, volcanic activity, and sediment deposition. Yet on human timescales, the act of mapping it remains a patient endeavor. Pulse by pulse, swath by swath, the hidden terrain becomes clearer. There is no single moment when the task is complete. Instead, it proceeds incrementally, guided by the same curiosity that first led sailors to lower weighted ropes into the water. Today, digital maps of the seafloor can be displayed on screens with shaded relief and contour lines. Mountain ranges run across ocean basins. Trenches curve along plate boundaries. Plains stretch outward from continental margins. These images represent centuries of accumulated measurement, from lead lines to multibeam sonar and orbiting satellites. Yet the ocean itself remains vast and deep. Beneath the shifting surface, darkness persists. Pressure still rises with depth, and light still fades within the first few hundred meters. The tools have improved, but the environment retains its scale and quietness. Ships continue to move across the water, sending sound downward and listening for echoes. The story of mapping the ocean floor is ongoing. It unfolds without urgency, guided by careful observation and steady refinement. What was once invisible has become measurable, though not entirely known. The seabed, shaped by forces within the earth, lies beneath layers of water that soften its presence from view. And so the process continues, ship by ship, expedition by expedition. Instruments transmit pulses into the depths, and echoes return with information carried in sound. Charts grow more detailed. Gaps grow smaller. The ocean floor, long hidden, is gradually traced with increasing precision. Still, much remains to be surveyed. The work proceeds quietly, in rhythm with the steady movement of the sea above. Thank you for spending this time exploring the quiet history of how the ocean floor was mapped. The story moves slowly across centuries of patient measurement, and it is a calm reminder of how much can be learned through steady observation. If you find these gentle journeys through science and history helpful for rest, you may consider subscribing. There will be more long, unhurried explorations of subjects that reward careful attention and a calm pace. For now, let the mind settle. The oceans remain vast and deep, and the work of understanding them continues in quiet increments. There is no need to follow it further tonight. I wish you a peaceful evening and a very good night.